Welcome to the Explainer. Today, we're doing something a little different. We're not just going to explain a topic, we're going to solve a crime. We'll be investigating a mobile app that's performing so badly, it's criminal, and we're going to uncover all the clues to make it fast again.
All right, so as the quote says, it's time to put on our detective hats because we've got a real crime scene on our hands. The victim, the user experience. The culprit, a slow, freezing Delphi Android app that users are abandoning in droves. Let's get to it.
Okay, so like any good detective story, our investigation starts right at the scene of the crime. And for our app, this scene is just littered with evidence of terrible performance. But there's one key piece we need to look at first.
And here it is, the application not responding warning. This is basically the culprit's calling card, left right at the crime scene. It's what happens when your app's main thread, the thing that handles all the user interface stuff, gets so busy, so completely blocked, that the Android operating system itself just gives up. It throws its hands in the air and says, nope, this app is frozen. This is our smoking gun, our first big clue.
But here's the thing, right? Your users, they're not going to send you a bug report saying, hey, I got an A&R. They don't use that kind of tech speak. What they say is the app feels broken, it's laggy, it's unresponsive. You know that feeling when you're scrolling and it just kind of hitches and stutters? Well, that's what developers call jank. And it completely shatters that illusion of a smooth, polished app.
So, okay, the app feels janky. Why does this really matter? I mean, this is where our investigation has to go beyond just the code, right? We have to connect this technical problem to the real world, to the business side of things. What does a slow thread actually cost you?
It means this. Look, a product director, they're not losing sleep at night because you dropped a few frames. But you know what they are losing sleep over? That user abandonment rate, especially in the first 10 seconds. Bad performance isn't just a technical problem. It's a direct line to people hitting that uninstall button. And trust me, they are never coming back. So, why is this happening? Well, it all boils down to a race against time. A really, really short race. To get that silky, smooth, 60 frames per second experience that we all expect, every single operation, every calculation, every pixel drawn on the screen has to be done in just 16.67 milliseconds. I mean, that's faster than you can blink. If you miss that deadline, even by a hair, poof, you drop a frame, and the user feels it.
And just when you think that's tough, guess what? It gets worse. On all of these new, fancy 120 hertz screens, that tiny time budget gets sliced in half. Now you have just over 8 milliseconds to do everything. Think about that. All those tiny little performance issues that you could maybe get away with before, now they're not so tiny. Now they're glaring, app-breaking problems. All right, so we know the constraints, we know the stakes. It's time to bring in our prime suspect for interrogation, the main UI thread. I mean, it's responsible for everything the user sees and touches, so if something's going wrong with the feel of the app, this guy has to be involved.
So think about this. Your phone today is a powerhouse. It's got multiple processor cores. 8 is pretty standard now. But here's the catch. The main thread, our prime suspect, can only run on one of those cores at a time. So if you're piling all your work onto that one thread, it's exactly like this quote says. You've hired a whole orchestra, but you're making the first violinist play every single instrument's part. It's insane. You're letting almost all of your phone's power just sit there, doing nothing.
And one of the biggest mistakes we see, a classic rookie move, if you will, is using something called T-thread synchronize. What this does is it tells a background worker, hey, stop everything you're doing right now and wait. Just wait until the main UI thread has a free moment for you. It's like telling a Formula One driver to pull over and wait for a pedestrian to cross. It completely kills the momentum and creates this massive, unnecessary bottleneck. The better way, T-thread Q, is like sending a text message. The background thread just sends its update and keeps on working. No waiting. And when that background thread is forced to wait, deep down in the system's guts, it creates something called an atomic lock. The easiest way to picture this is to imagine a stadium trying to let everyone out through a single tiny turnstile. It doesn't matter how fast people can run, everyone has to line up and wait their turn, one by one. And all that productive work just stops, dead in its track. Okay, so we've got our main suspect, the UI thread, pretty much cornered. But you know, in any good crime story, the mastermind rarely acts alone, and our investigation is revealing that the main thread has a couple of accomplices. Let's unmask them. Accomplice number 1. Bad memory management. So in some older systems, there's this thing called a global lock on memory. What that means is only one thread can ask the system for more memory at a time. It's like having a single librarian for the entire world. Every single thread has to get in line and wait its turn just to get a little bit of RAM. You can imagine how that brings a super fast, multi-threaded app to a screeching halt.
Now, accomplice number 2 is the one you never suspect. It's the inside man. It's actually the very thing that makes FireMonkey so powerful and flexible. Its styling system. Yeah, the thing that lets you create these beautiful, custom-looking apps. It turns out that flexibility comes with a very, very high price when it comes to performance. See, a list item in FireMonkey isn't just one simple thing. It's a whole collection of pieces. Rectangles, text labels, maybe some effects, all put together just to make one row in a list. Now, that's great for making things look pretty, but it's a disaster for speed. Because every single time you scroll, the app has to destroy the old items and then painstakingly rebuild the new ones from all those little pieces over and over and over. And with every rebuild, it's just chewing through that tiny 16 millisecond time budget we talked about. So after interrogating our main suspect and unmasking its accomplices, we finally have our big breakthrough in the case. The solution isn't about trying to make one thing go a little bit faster. It's about a fundamental shift in thinking. We have to stop thinking one step at a time and start using the massive power that's already sitting right there in our hands.
We're talking about parallelism. Instead of giving one core a huge job, like processing a big image, what if we split that job up and give a little piece to all the cores at once? Well, the result is just staggering. We're talking performance gains of up to 700%. A task that took 8 long, agonizing seconds can be done in just 1. That's not an improvement, that's a transformation. And that is the difference between a user getting frustrated and deleting your app and a user falling in love with it.
And this leads us to the most important clue of all, the real moral of our detective story. Performance isn't something you can just bolt on at the end. It's not like adding a fresh coat of paint. It has to be baked in from the very beginning. It has to be by design, not by accident. You have to be thinking about parallelism and performance from the moment you write the first line of code. All right, we've cracked the case. We've found the culprits. So what's the verdict? Well, let's take everything we've learned and put it into a simple, actionable playbook. This is your guide to solving performance crimes in your own apps.
Here it is, your 4-step plan. Step 1. Audit your threads. Go on a search and destroy mission for those blocking synchronize calls and replace them with queue. Step 2. Optimize your list views. Make them smarter so they don't have to rebuild everything all the time. Step 3. Audit your FMX styles. In those long, scrolling lists, simplify. Go for lightweight and fast. And step 4, probably the most crucial rule of all, measure, don't guess. Use a profiling tool to find the real bottlenecks. Don't waste time fixing things that aren't actually broken.
And this whole investigation leaves us with one final and maybe a little uncomfortable question. A question that every single developer has to ask themselves at some point. If you have to fight this hard, if you have to dig this deep into system-level tricks and optimizations just to get good performance out of a cross-platform tool, at what point do you stop? At what point do you ask, wait, would it just be easier to build this natively? There's no easy answer. It's all about trade-offs, architecture, and knowing when the fight is actually worth the reward.